are the Fluid Power Vehicle Challenge team. My name is Abel Backus. I am the team lead.
I'm Jacob Gaddick. I'm the regenerative braking lead.
My name is Ethan Hunt. I'm the pneumatics and electronics lead.
Tom Pollock, fabrication lead.
Emily Hintz, I'm the frame design lead.
So we're going to start off here. This is our project statement. I'll read it out to you so you kind of get an idea of what the goal of our team is. So the goal of this project is to design and develop a vehicle that combines human power with fluid power to propel a vehicle. The project provides us with hands-on experience, both engineering with the engineering design of all the hydraulic circuits and components, and then combining them in a frame together, and also giving us expertise in the manufacturing and how fluid power is applied.
So the main objectives we wanted to achieve with this competition were place top 3 in the region in endurance race. Then also we wanted to create a compact hydraulic design to minimize any losses in the hydraulic system that we can. The next one we want to do is incorporate a unique pneumatic design, and then an easy to use electronics. That way everyone on the team could use the electronics and also help out with any electronical issues and continue with the use of electronics for ease of use and everything like that.
So for our background research, we started with looking at last year's design. So you can see here it's the standard bicycle they have pneumatic stabilizers. Two-wheel bike, obviously. They have a custom hydraulic reservoir stored in the frame in front of and underneath the rider. Everything else is stored behind the rider on a little cage back there. So taking inspiration from them, we saw a lot of good things that they did. Specifically, we're using the same accumulator. It is not in production anymore. You can't get them, so we're going to reuse it. The advantages of it are that it's super lightweight, which helps us reduce the weight of our vehicle. They did have some issues with their chains, and also their pneumatic stabilizers did not work particularly well. So we decided that we would appreciate the work they've done and then create our own design as opposed to taking their design and improving upon it.
Right, adding to our background research, the NFPA provides a list of all the previous contestants and what they did for the previous year's competition. So looking into some of the designs we had, some of the designs they had, a lot of them were 3-wheel vehicles, a lot of them built from existing bike frames, recumbent bikes, or otherwise modified from a bike frame. For those that made a custom-built frame, T-slot aluminum was their go-to material. On top of this, there was a pneumatic component into the scoring of vehicles, and so looking at the applications of these other teams was important to us for scoring. We saw a lot of teams using pneumatics for a suspension system. One team used a pneumatic clutch that I believe won them the pneumatics award for that year. There were also common uses of jacks and center stands with pneumatics, as well as notably with the MSOE team, the pneumatic stabilizer. Something else to look into was our electronic system, and in other teams, they were using PLC and HMI in their electronic systems to really score those points in the electronics. Common things were LCD sensor readouts, hydraulic controls, ergonomic and mounted onto the handlebars, as well as solenoid valve control included on those. So expanding into our designs, as we sort of brainstormed and generated what we would be building, our first design note would be taking a pre-built tricycle frame and then sort of cleaning out the back to mount a large build plate for ease of assembly and ease of use in our hydraulics. We would also use pneumatics to act as a suspension system for the front wheel. And we would make sure to keep all of the hydraulic components behind the rider, one for safety and two to keep all the lines from accumulating losses from large travel distances. So if you keep the hydraulics all in one spot, then you lose all of those losses, the system becomes more efficient. Some of the drawbacks to this approach would be that since the frame is fixed from an existing tricycle, that it would be hard to adjust the frame or geometry if need be for hydraulic components. And being an existing frame, we can't choose the materials, so there's a weight concern there. Our second design is a recumbent bike made from aluminum 80/20 extrusion. The main benefit to this design being that it's more customizable. With T-Slot, we're able to move the frame around and hit dimensions that we might need later on that we didn't account for. By lowering the center of gravity, it also increases safety for the rider and makes the design overall more stable. We're also aiming to keep all the hydraulics in the same spot behind the rider for ease of maintenance and for safety. And using aluminum, we can guarantee that the design is a lighter weight. However, since we are, in this case, building our own custom frame, we do need to account for build time for that, so that will increase the overall effort required to build this vehicle. And we would also need to separately design steering and braking systems, since if you were going with an existing bike frame, then those would just be on bike. We would have to, from scratch, design braking and steering. Our third notable design takes an existing upright two-wheel bike frame and converts it to a tricycle by removing the back wheel and adding an axle that can support two wheels. We would also be implementing a flywheel so that as the rider pedals, if they happen to get tired or change speed during the endurance or regen races, they would be able to store power and travel at a more consistent speed, as well as store power if they were to use the hydraulics. That would aid in the regenerative braking because the flywheel could store energy on top of the accumulator. Some of the drawbacks with this are we now have a giant hunk of metal spinning at high speed on a bike, and we need to account for safety concerns with that. So we would need to have a brake on the flywheel as well as have some sort of cage to contain it in case of catastrophic failure. In adding a flywheel, that would also add weight to the vehicle on top of using a bike frame, which we can't control the material. We also need to implement a pneumatic clutch, and that will aid performance. However, it will also add to our lead time. Our fourth design, the most creative of the bunch, being a treadmill. So we would be from scratch building into the frame a treadmill and using a belt to supply power to the hydraulic motor. We'd be raising the platform on standard size 26-inch bike wheels so that there would be space underneath to mount the hydraulic components. And we would also be using a wheel up top on the frame to steer. So the drawbacks of this design being that since you are high up and you're in a standing position, there are safety concerns with mounting and dismounting, especially during the endurance race where we will be regularly switching riders. There's also limited space. We do have space underneath, but we don't know if that would be enough to support the entire hydraulic and pneumatic systems. This will also be difficult to assemble as we're building from scratch, and it's very far out from a standard bike or vehicle design that we've seen in previous years. And on top of that, we are unsure of the feasibility of the treadmill being able to deliver that amount of power to the hydraulic motors without slippage.
So after considering all these designs, we had a lot more, but we figured we'd spare you that and just go through 4 of the important ones. We scored all of these based on weighting criteria that you can see on the left there. The big ones being speed, regen, and endurance. Those are the races we will be competing in. And each of the designs were put through this, and we have, these were all the highest rated ones. And then we included the treadmill to show that even though it may have been the most innovative design, its practicality is on the lower end. These were rated on a scale of 1 to 5, 1 being non-functional and 5 significantly exceeding our expectations for these categories. So rather than choosing any one of those previous designs, we chose a different approach where we took the highest rated parts of each of these designs and put those together to create what you see here for our finalized design. Some of the big things that we took away from our design process would be that we would want to incorporate the flywheel. That was a very innovative feature that we'd come up with. It wasn't something that was done by many previous teams. We wanted to keep a tricycle for stability reasons. And then given that we use the flywheel, it made the most sense to mount all of our components in front of the rider because this minimizes the losses in our systems. But because of this, it means we're going to have a rear wheel steering system, which, as you can see there, is the rider would grab that handle there. There would be a vertical angular displacement, which then translates to a linear displacement, and finally, the rear wheel would receive the final angular displacement. Yeah, I think that's, and then our hydraulic system.
Yeah, so the hydraulic circuit is kind of the main big part of this competition. The goal is to make this hydraulic circuit. So working with some of our technical liaisons and our industry mentor, we came up with this hydraulic circuit. So I'm going to run through kind of the different modes that we have and how they might work. So part of the race, or part of the sprint race, is that you can pre-charge the accumulator to give yourself a boost to get started. The hydraulics do not function very well with human power, so having that extra boost allows you to kind of get moving and not spend the first 5-10 seconds of the race with everybody just pedaling. So with that in mind, we have here, we'll go straight from the reservoir through the pump straight to the accumulator. The default of the system would have this valve open, so when we want to charge the accumulator, we will activate the solenoid valve, which will prevent fluid from flowing back to the reservoir, and we'll go straight to the accumulator, allowing us to build up charge. Then if we want to just power the motor, we activate this first valve, which will take us directly up to the motor and then down back to the reservoir. Very simple. Part of the race is the regenerative braking. So when we're doing that, we need to have a way for the motor to pull fluid, which is why we have this check valve coming from the reservoir that will allow the motor to pull fluid. And by activating this valve here, it will run up and it will go into the accumulator. Then once we've built up charge in the accumulator, we can activate this solenoid valve, which will allow fluid to flow from the accumulator back down through the pump and down to reservoir, allowing us to run purely off pre-built accumulator. Just a couple interesting notes. We have required points for testing, so we'll both have gauges there, which is part of the requirements, both for safety and to check, test how the system's working as we're constructing it. We also have an orifice here, which will be used for if we're in our testing, if we build up charge in the accumulator and we want to be able to dump that charge without powering the motor or sending it through a part of the system that we don't want it to, we'll be able to open this up, and that orifice will prevent the accumulator from dropping all of its charge all at once, which will protect our system. That moves us on to the pneumatics.
All right, so before we get into the guts of the pneumatic system, it's important to note the application that we're using. So since we are using a very different set of riders with very different leg lengths and different heights, our pneumatics will be used to adjust the dimensions of the seat. So we'll have a forward and back control as well as a angle of the back of the seat. So this top cylinder up in the top right, that will be going to the angle of the seat, and the bottom one going to the forward and back. Since those will both need different power applied to them depending on who's riding the vehicle, we have on the left side an electronically controlled pressure regulator. So that will allow us to send different pressures to each of these spring-loaded cylinders so that we can get a different displacement. We also have relief valves in place for safety as well as to dump excess pressure if you would like to go from full actuation back to a lesser actuation.
after we selected the design for our vehicle, we had to make some vehicle calculations in order to not only set goals for ourselves, but also to size components. So the first few equations that we have been provided by the National Fluid Power Association. It was just the baseline in order to get some calculations done. So first off, at the bottom, we have a simple free body diagram of the worst case scenario of how it's going to go for the race. As you can see, there's an angle theta. We're not really focusing, or there's not a major difference in change of angle. So it's going to be a relatively flat race, but we still have to consider it for worst considerations. So in order to get that angle, we heard that there's going to be a 3% grade on the track. So we take the arctangent of that and see that the maximum angle that we're going to reach is 1.71 degrees. Next up, we have an acceleration force. This was just a standard that was decided by the team. So the simple calculation for force equaling mass and acceleration, we get a final value of 11.81. The number 380 comes from our minimum or maximum weight of the vehicle added on to the maximum weight of our driver. So our specification for that, we wanted to have a 180-pound bike, and I weigh the most on the team, so you add 200 to that to get 380. Next up, we have the pole force. So you can take the sine component of that and as well as multiply the weight to get a value of 11.39 pound force. And next up, we have rolling resistance. This has to compensate for when we're going uphill and just some gravitational forces that are compensating for us. So we take the cosine component of that and then multiply it by R. This was a frictional constant provided from the National Fluid Power Association, which was 0.002, to get a final force of 0.759. And lastly, we sum up all the components in order to compensate for that to get a total of 23.97 pound force. After those calculations, we did sizing component, minimum size for our components that we need to get. So we first do torque from the wheel. So we multiply it by the radius of our wheels. We're going to do 26-inch diameter wheels. Those are standard for most bikes. So that's the number that we selected. We got a total torque of 311.54 pound force inch. And next up, we have sizing our drive motor. This equation was also provided by the National Fluid Power Association. CIR is cubic inches per revolution. So we had that set equal to torque in order to get it by itself. And then we find out we need a 1.3 cubic inch per revolution motor. However, there may be some inefficiencies. We can't always guarantee that our components are going to be the most efficient. So we compensated, saying it's only going to be about 90% efficient to get a CIR value of 1.45. The next thing we have is wheel RPM. So we take 336, that's a constant provided from the NFPA, and we multiply it by our maximum miles per hour that we want to reach. One of our goals is to reach a maximum of 25 miles per hour for our vehicle. So we multiply it by that and then divide it by diameter, simply to get an RPM of 323.08 to the wheels. Next up, we have our motor, which is measured in gallons per minute. So we take the cubic inches per revolution and then multiply it by the RPM divided by another constant that was provided, 231, in order to get 1.82 gallons per minute. Lastly, account for inefficiencies. The motors are usually 95% efficient, so we divided by that inefficiency to get 1.92 GPM. The next thing we have is our sizing for our hoses. So we have the line sizing for 20 feet per second. per net area. So we take 0.32 and multiply by our GPM and divide it by 20. 20 is a feet per second of net area, and we get a value of 0.031 inches squared. Next up, we have a pipe or a pump line for the 20 feet per second net area, and this was another equation provided by them. Just take the square root of 4 over pi multiplied by our line sizing, and we get 0.198 inches. We did the same thing for our 5 feet per second net area to get 0.123 and 0.396. And in order to get our pump sizing correct, it was a similar equation, but just for the pump to get 0.131 cubic inches per evolution, and then lastly, accounting for inefficiencies at 1.37.
So moving on to the flywheel that we want to use. So part of the competition is to innovate and find new ways to do cool stuff. So we wanted to implement a flywheel. In the rules, you are not allowed to have extra energy sources such as batteries or internal combustion engines is specifically disallowed. They want all the power that's put into the system other than for, solenoid valve controls to be from the rider. So looking into the rules, we said, okay, we can put in a flywheel. As mentioned before, the benefit of the flywheel is that, especially for a longer race, as you get tired from pedaling, maybe, you're going at 80 RPM, then 70, then 75, you're kind of fluctuating. And so to keep a steady input to the system, that we would have the flywheel, which would help regulate that input, give us a nice steady flow. It also allows us in the endurance race, when we come to a stop, we can set the pump to just circulate to the reservoir, and that allows us to keep the flywheel spinning, and it gives the next rider a little boost at the start to get them going. We also have what we are tentatively calling launch control, which is would be allowing the flywheel to spin freely, again with the pump just recirculating to the reservoir. That would allow us to put all of the power that we can generate from our legs to spinning that flywheel up to speed. And then by manipulating the valves appropriately, you can kind of jump start the system like you might in a car in a manual, where you get it up to a higher RPM and then kind of smoothly let out the clutch, let on the gas, and that'll allow us to get a good start, and we don't have to kind of struggle at the very beginning. So when we brought this up to the NFPA and the technical liaisons, we said, here's our idea. They are tentatively okay with it. They said, if we're going to include it, we need to have a brake system on the flywheel to make sure that it's not spinning, especially at the start of the race. They don't want us to have an extra advantage of a flywheel that's spinning. They also want us to be able to verify that it stops. That would both be with the brake system, and then we'll add the tachometer, which would allow us to say, here, it's not moving, but also give us kind of test data. And then also, they did not specifically give us any requirements on safety other than saying it needs to be safe. So we're looking into having a solid angle iron frame around the flywheel so that in the worst case scenario that it comes off the shaft it's spinning on, it can't come out and hit the rider. Last week, we had a presentation for the NFPA and the whole association, kind of just similar to this where we're explaining what we're doing. We were working, our technical liaison is on board with the flywheel, but in talking with some of the others, they were not so certain that they wanted to allow this. So this feature, we've done a bunch of calculations on, we're ready if they allow us, but it might end up getting scrapped. So getting into the flywheel calculations. So we want to calculate what torque we can apply to the flywheel. We did that by applying a 0.9% or 0.9 efficiency. So that's a rather large value accounting for any losses in the system or any other inconsistencies in our in our system. By knowing that the torque of the flywheel is the moment of inertia times our angular acceleration, we can calculate how fast the flywheel will be going with our applied torque in a certain amount of time. So we said this is specifically for the launch control. We wanted to apply our maximum torque for 5 seconds. And then we wanted to make J such that we could have about 1,000 RPM on the pump. Hydraulic pumps and motors are designed to be run with oftentimes, a full diesel engine or an electronic motor that can easily maintain 1,000 RPM at multiple horsepower, whereas a human can only put out about 80 RPM at a fraction of a horsepower. So by spinning it up, this allows us to kind of sit in that, for our initial boost, that allows us to kind of sit in that higher efficiency zone as we get moving. So with that in mind, we're able to calculate J. We said we want our radius to be less than 5 inches. That's both for safety and practicality. If you have a flywheel that's any bigger than that, it starts to get very unwieldy. You start to have, you really will have to take into account the gyroidal effects of it. And for the thickness of the flywheel, we want it to just be a generic, easy to get plate steel thickness. That makes it easy for us to manufacture, it reduces cost. So with those numbers, we calculated that our radius would be 4 1/8 inches radius by 1/4 inch thick. That gives us about 4 pounds mass and a omega of about 978 RPM.
So, and then the second case we wanted to look at was after we unload, or after we get past this charging phase, and we actually dump that pressure we built up and the energy and flywheel built up to the motor and to the pump. We're going to calculate what will that actually be after we reach a steady state value. So this will be for the endurance race. We've been pedaling for 2 minutes. We're at a steady point where everything is equal to each other, and we can continue from there. So we analyze the torque of the system itself, realizing that the flywheel will be the efficiency times its J value with the angular velocity. With a steady state assumption, we can assume that the angular velocity will be 0. So with this, we can just assume that the torque of the system is equal to the input torque of the rider.
So the beginning of our calculation section, we talked about the CIR values that we needed for our pump and motor. This was all leading up to our pump and motor selection. This was the pump we ended up selecting with a 0.659 CID. And on the right there, you can see the dimensions of our pump. This is the motor. Similarly, we have a 0.513 CID. And once again, those are the dimensions. These were selected off of the SunSource component selection sheet. And yeah, there's the serial number there, and these are the components we're going to be using. We also picked our pneumatic cylinder. This was once again, our requirement here was based on the height differences of the riders. So that required us to have a 4-inch stroke, which led to the selection of the one you see on the left there. And then that is where on the CAD model, it will be mounted under the seat and then behind the rider.
So for the electronics, we ended up choosing a Raspberry Pi 3 Model B, specifically as it'll be able to plug directly into the LCD screen that we chose. This is just for ease of use and easy programming. Also for simple wiring with the Raspberry Pi 3. And then it's also direct plug and play, as I had experience with Raspberry Pi software and using Python. And I believe we can also code in C++ using this model. And I think we have time if we work with C++ too. So we have very easy to use, well, the LCD will allow us to have easy to use electronics, and then also we'll be able to have an easy time coding, at least with the Raspberry Pi.
So to summarize what we accomplished for our first semester, just basically a schedule that we had for ourselves. We created a team and did some research for the rules of the challenge, as well as any background research on previous designs from other colleges. Then we had our vehicle design brainstorming, as well as circuit creation. And then after that, we did component sizing, doing the calculations, and as well as selecting our components. And then our last step was to finalize our purchases for the components and then prepare for a review. Now, some goals for the second semester, these are kind of arbitrary. We just have it due on the first of few months, so we're gonna fabricate the frame as well as create the electrical circuit at February 1st, and then have our hydraulic and pneumatic circuits finished a month after. And hopefully to have our vehicle completed for March 15th, because we have to, our competition date is in April, so we have to do that by then.
All right, that's what we've got. What questions do you have for us?
I have a question. For the seat adjustment, did you consider like just a mechanical solution? Why do you have to use? Did you have to use pneumatics?
So it's a fluid power challenge, we'll say. So you're required to use hydraulics to propel the motor, and then there's additional rewards for how you implement pneumatics, which is why they're so varied. So we decided that's how we wanted to implement pneumatics and add that to our system.
As stated before, we wanted to initially have a pneumatic clutch on one of the designs, but we thought that this would be a simpler implementation for the pneumatics.
So you thought about using three-way valves for that rather than two-way valves?
Yeah, so that was an issue I ran into. I was trying to make it work with the old, it's a four-way 5-position valve that the team used last year. And I ran into an issue where I could not dump one cylinder and, I couldn't feed one cylinder and let me backtrack. I would pressurize one cylinder and dump the other cylinder. And so I just ended up choosing just the 2-position 2-way valves, because then I can just control those individually. And my plan was to depressurize one side and repressurize it, and repressurize the other side. So if I have, let's say I'm switching from Emily to Jacob, I can just pressurize the length, depressurize the angle, and do it that way was my plan.
Part of the issue also is that unlike, simple electronics that some teams are using, especially hydraulic and pneumatic components have a much longer lead time. Most companies aren't building a hydraulic circuit in 2 weeks. So there's a kind of a select group of components that we can choose from. So we were limited there.
Yeah, that was why I made the suggestion. Three-position valve is the standard in industry, so they're going to be available all over the place.
Yeah. And that's what I was running into. I just couldn't find one where I could actually pressurize one side without depressurizing the other side. And there's certain cases where we might not want to do that. Let's say Abel wants his angle at roughly 50 degrees and Tom likes that angle too. I want to keep that ability so I can keep the angle the same pressure and not have to change that and just be able to change the length only was my concern.
I just had a quick question. So I was curious about how the different aspects of the competition. I mean, there is the race, right? And then there also, it sounds like you have additional credit for pneumatic capabilities. I was just curious, how do they control for a difference of, let's say you have like a team from Colorado that also happens to be professional cyclists, and then we have like, another school would make you study for 22 hours a day. So, but I was curious, like how they control for that factor that may not really be designed.
Yeah, so there's lots of different awards. So I think in the interest of bringing people into fluid power, there's rewards for the midway review. So if you did really well in the midway review, even though your vehicle might not move at all, which happens to some teams, maybe you still did good in the midway review or the final review. They also have rewards for your electronic implementation, the pneumatics, like we mentioned, and also just like a overall judges award for what they thought was best. So on the one hand, yeah, they don't really account for, some teams have 15 members plus 4 faculty advisors plus their industry mentor, and some teams have us who have never touched fluid power until this, but they try to make it at least somewhat engaging for everyone.
There is also a separate race category entirely is running just off of your hydraulic circuit with a pre-charge.
Oh, okay.
So if you aren't the most athletic, you can still sort of have your bike carry you through that race.
That's why we were focusing on the region as well, because that's what that race is, yes.
There is definitely an advantage if we were all D1 athletes, we would definitely do better.
They also weigh the rider.
Okay.
So the weight inside the spinal rider.
They do
Yeah. Yeah, I believe I would.
And have you tried the rear wheel steering system before? It's so different than almost any vehicle that we're commonly used to.
That was part of our reason why is that hitting that innovation factor will score you points with the judges. On top of the fact we wanted to simplify the front end of the bike so that the hydraulics and the steering system didn't interfere. So it was an interesting design choice that might have consequences later down the line, but we do have our reasons.
Yeah, we cut a lot of our losses out of the system as well, so that's hopefully gonna pay off in the long run.
Do you have any other questions? All right, guys, ready to clap? All right.
Gotta hit another presentation.
Yeah.
I forgot to mention this on you.